In this video, I'm going to tell you about the topic that won the last survey I proposed you: black holes. Don't worry if you have no knowledge of physics. This is just an introduction, and as usual in my science videos, I'm going to try to be as simple and as clear as possible. We're going to take things and concepts step by step, so that you don't need any particular knowledge to understand what follows. In case you are interested, I will also make versions of this same video in French and Spanish. They should be out in a few days. And in the description, you will find links to other science-related ASMR videos I made, like the one about the Big Bang or nuclear power. But it's now time for you to adopt a comfortable position. I recommend using headsets. I'm going to show you a few images as always, but you don't need them to understand what follows, so you may just close your eyes and let my voice guide you. To begin with, and before we arrive to black holes, we need to make a bit of history and talk about gravitation. You probably already have an idea about what gravitation is. It is a force that was theorized and measured for the first time about 300 years ago in the 18th century by British mathematician and physicist Isaac Newton. Newton is mainly remembered for his law of universal gravitation, and this theory, this law, states that all bodies in the universe attract each other. We all experience the gravitational force at any moment in our lives. This is what gives us a weight when we are on the Earth, walking on our planet. What we call weight is the gravitational force that pulls us to the surface of the Earth. And if we imagine that we go to space far enough from the Earth for its gravitational force to become neglectable, we would still be made of the same quantity of matter, we would have the same mass, but we would have no weight, because the Earth would be too far to give us a weight and pull us to its surface. That's a good occasion to explain the difference, the little difference, between the terms gravitation and gravity. Gravitation is this general term that describes the attraction of material bodies between them, whereas gravity is the particular gravitational force exerted by the Earth on anything on its surface or close to it. So in a sense they are almost synonyms, but gravity is theoretically limited to the gravitational force of the Earth. This gravitational force is crucial to understand how bodies move in space. This is what determines how a satellite like the Moon orbits around a planet like the Earth, how a planet can orbit around a star, how comets are traveling in space, how solar systems are orbiting around the center of the galaxy they belong to. The discovery of gravitation raised plenty of new questions in the scientific community in the 18th century. Newton had proved that the bigger a body was, the more massive it was, the stronger the gravitational force it would exert on everything around it. So it meant that if you wanted to escape the gravitational field of a particular body, you needed a force to compensate for it. This is what a rocket makes when it is sent to space. The burning of its fuel gives it a thrust that is sufficient to offset the gravity, the gravitational force of the Earth that tries to make it fall back to its surface. Of course, in the 18th century, the idea of leaving the Earth was purely theoretical, but this is the moment when the prerequisites started to be elaborated by physicists. And they realized that given the existence of the gravitational force, an object that would try to escape, to break free from the gravitational attraction of a massive body, would need a lot of speed, or in physics terms, a lot of kinetic energy to do so. Now, just imagine you throw a stone towards the sky. When you throw it, you give the stone energy, a kinetic energy, which makes it rise above your head, and you know that a moment later, a few seconds later, it's going to fall back, and it falls back because the gravitational force of the Earth is more powerful than the energy you gave to the stone. But if you increase this energy, if you give it more speed, maybe the stone could go far enough to break free from the gravitational attraction of the Earth. And this speed, this energy you need to reach to beat a gravitational force is called the escape velocity in physics. Of course, the bigger a body is, the higher the escape velocity is going to be, because the gravitational force is more important. If you take the example of the Earth, the escape velocity of the gravitational field of the Earth is about 11 kilometers, that's about 6-7 miles per second. If you take the Sun, which is much more massive, the escape velocity is more than 600 kilometers per second. So, returning to our example with the stone, if you manage to throw a stone and give it a speed of 11 kilometers per second, you can try, I don't think you will succeed. The stone is going to leave the Earth and escape its gravitational field. Now the concept of escape velocity assumes that there is no additional thrust, additional propulsion. It is the speed that at some point an object needs to reach, but it is perfectly possible to escape the gravitational force of the Earth without reaching this speed if you keep benefiting from more thrust, which is the case for a rocket that continues to burn its fuel. It is also in the 18th century that physicists started to approximate what is, to our knowledge at least, the fastest possible speed in the universe, the speed of light. The speed of light, which is close to 300,000 kilometers per second, is obviously much higher than the escape velocity of the Earth or the Sun. But a theoretical question appeared in this period. What if an object in the universe, a body, was so massive that its escape velocity would become higher than the speed of light? Theoretically, it would mean that even light could not escape from its gravitational force and would stay prisoner from it. It took us 10 minutes, but here we are. This is what a black hole is. A body that is so massive that even light cannot escape from the gravitational force it exerts on everything around it. In a sense, it is rather misleading to call this a hole. It works if we consider that a black hole is so massive and has such a powerful gravitational force that it is going to absorb any matter and everything around it. But it is the opposite of a hole, given that it is intensely full, intensely dense and massive. During the entire 19th century, this theoretical concept of black hole, which was not even called like that, the term black hole appeared in the 1970s, it is quite recent, did not particularly evolve, and one big difficulty that physicists are still facing is that it is difficult to observe an object that absorbs light, because by definition it's entirely black and cannot be seen directly. But at the beginning of the 20th century, a new revolution happened in physics with Einstein's works and his theory of relativity. This is a completely different topic, and I finally decided to not talk about it. To keep things simple, I'll probably make another video about Einstein's work at some point. But let's just say that the theory of relativity and Einstein's vision of physics revolutionized everything and made the law of Newton, the law of universal gravitation, appear obsolete when it comes to describing the universe on a large scale. In Einstein theory, gravitation becomes a consequence of the curvature of spacetime by massive objects. Once again, we will talk about this particular topic another time, but interestingly, Einstein theory predicts the existence of black holes, and this sparked much more interest in them in the 20th century. Theoretically, because this remains controversial, Einstein's works and additional works by other physicists in the 20th century predicts that the light absorbed by black holes could be rejected somewhere else in the universe at a completely different point in what is called, and that's purely theoretical, white holes. And the way between these hypothetical black and white holes would be called a wormhole. This has quickly become very popular in science fiction, even though that remains purely theoretical and nothing of that kind has ever been detected. But this opens a lot of possibilities in fiction, like instant travel from one point to another in the universe, and this is why this has become a part of popular culture. But these themes on purely scientific grounds remain very uncertain still today. On the opposite, the existence of black holes is no longer in question, as they have been indirectly observed, because the biggest difficulty when it comes to proving the presence of a black hole somewhere in the universe is that they are relatively small comparatively to their mass, and they absorb all light, so they do not emit any, and it's complicated to observe them directly. But a black hole impacts its environment, and this is how they can be detected. For example, at the center of a solar system or at the center of a galaxy, if astronomers observe that many bodies seems to be revolving around nothing visible, this certainly indicates the presence of an extremely massive body that rejects no light, and that has to be a black hole. There is probably at the center of our galaxy a very massive black hole, and the entire galaxy is revolving around it. Another indirect observation method is to detect how light is going to be deviated, perturbated by the presence of a black hole and the intense gravitational force it exerts on everything. A bit like when you are looking through a window outside and you see the trees or leaves moving because of the wind. You're not going to see the wind, you're not going to experience it directly, but you know there is wind because of the move in the vegetation. And this indirect method that uses the process called Doppler spectroscopy. I talked about the Doppler effect in the video about exoplanets. I put the link in the description. Is a good way to make sure a black hole is present in one particular place in the universe. How can black holes appear? Because we need a huge concentration of matter in a relatively small space to see a black hole happening. Probably for the most massive of them, with the depth of a supermassive star. When a star dies, when it has exhausted its fuel, you know that it may collapse on itself and become a much smaller body. And provided this body becomes dense enough and remains massive enough to attract everything around it, it can turn into a black hole. Once it has appeared, a black hole tends to work like a giant vacuum cleaner. It attracts all matter that is close enough to fall into its gravitational field, and bit by bit the black hole can only grow, add more matter, and become more massive. What we would be able to see if we approached a black hole and if we could enter it is also something quite mysterious at this point. First, because in the center of a black hole there should be like an intensely dense planet, a black planet, made of all the matter that the black hole has absorbed and constantly growing. And around this black planet, a halo, and this is this halo that we call the black hole, in which we are close enough from the planet for light to be absorbed. So this black thing we see when looking at a black hole is not entirely made of matter. It's the halo around it, in which the gravitational force is strong enough to absorb the light. And this limit around a black hole is called the event horizon. The event horizon is the limit after which it is no longer possible, even at the speed of light, to escape the gravitational field, to break free from it. But at the center of this black and immensely dense planet, the laws of physics as we know them at this point are unable to describe the forces, and this is what physicists call a singularity, a place that we can not really understand and describe even theoretically, because in a singularity the curvature of space-time becomes infinite, and this is something the theory of relativity cannot describe correctly. Maybe in the future, and especially with the development of quantum gravitation theories, it will become possible to better understand and theorize what is a singularity. But even the most recent theories are not there yet. Well, I hope this little introduction gave you a better idea of what black holes were. It opens many other doors that I hope we can continue to explore together in other videos, like the theory of relativity or quantum physics. But I'll see you another time to talk about them. Thank you very much for your attention. As always, your comments and ideas for future videos will be highly appreciated. And see you soon for a new video.